Okay, this is the second part of our lecture on Fermi gas. So, in this part, we are going to talk about particles and holes. So, as I explained before, once we start increasing temperature from the absolute zero, some fermions want to leave the Fermi sphere due to their kinetic energy or thermal fluctuations. And there is a convenient way to describe such states using holes. So let me just demonstrate it using this picture. So imagine this is our Fermi surface, and let's assume that one of the fermions have enough energy to escape the Fermi surface and become, for example, a conducting electron in metal. So as a result, there is one fermion missing in the Fermi, under the Fermi level, and we call it a missing fermion as a whole. If we increase the energy or temperature, if we decrease the energy or temperature, then the particle or fermion can come back and join with the whole and annihilate it. As a result, this holes and particles, they form pairs, which once you decrease energy, they will just annihilate each other. Okay. Okay. So the absence of a fermion of energy E, momentum P, and charge E corresponds to once fermion moved out from the Fermi surface, it corresponds to the presence of a hole of an opposite energy, opposite momentum, and opposite charge. Okay, so if, for example, fermions are negatively charged, then holes are positively charged. Of course, there are no real notion of a hole is basically a vacancy, but it's very convenient to look at them as particles under the Fermi surface, which just move exactly, can move exactly like similar to particles itself. But this is kind of, it's of course it's visualization only, but you can look at it as a kind of antiparticle, okay, with opposite energy, momentum, and charge. Since fermion occupation numbers, we know that there are only 0 and 1, so the number of holes is 1 minus the number of fermions, okay, for any particular state. So in a Fermi gas, in thermal equilibrium, so the average occupation numbers should satisfy the equation. Number of particles plus number of holes for any particular energy level should be equal always to. Okay, so we know that particle occupation number is given by this formula. So if we calculate 1 minus np, which is the particle occupation number for a hole, then you can get the following expression with mu and energy interchange. So you see that when an excited fermion so as I said, when an excited fermion falls into an unoccupied state, a particle and a hole, they annihilate each other, and in this sense, a hole is an antiparticle. Okay, this concept works only for low temperatures, where there are relatively few particles and holes participating in thermal activities. And as I mentioned, that holes that have negative charge energy and momentum. And you can indeed see that if particle has positive charge and positive chemical potential, then correspondingly a hole has it then with negative sign. So you can indeed interpret the hole as a kind of a particle with negative energy and negative chemical potential. Okay, so now we are going to look at electrons in solids. And an electron in the solid, in the lattice of a solid, it moves in a periodic potential created by ions, and it experiences transmission and reflection as it travels. Okay, and for certain energy ranges, these directed and reflected waves can act coherently and produce a destructive interference. As a result, we see energy gaps in the spectrum of electrons, and the lattice acts like a band pass filter. You can actually see this happening if, for example, if you take a Schrödinger equation in the periodic potential and try to solve it numerically or explicitly, you will see that for some certain energy regions, that Schrödinger equation does not have solutions. So those energy levels are not allowed. There are gaps in the spectrum. And this is exactly happening, a physical explanation of that. This is what I just explained. And if you, for example, solve typical Schrödinger equation, so in many cases you will see a structure like that. So there is a band of allowed energies, one band showed here in the red, and then there is another band of allowed energies, and there is a gap in energies where this destructive interference of transmitted and direct waves basically cancel each other, and there can be no energy in this part of the spectrum. There cannot be energy states. Okay, but in here we need to consider three different situations: metals, semiconductors, and insulators. When the Fermi energy, so by the way, so let me introduce this notation. So this here is these three situations for fermions, and here in the middle by a dashed line I showed Fermi energy, and the band, allowed energies band below the Fermi energy is called a valence band, and where basically fermions cannot move because they are just frozen below the Fermi surface. And the gap above the Fermi energy is called the conduction band. Okay, and let's denote the top energy of the valence band as the energy epsilon zero. Okay, so when the Fermi energy is much less than the top of the valence band, so it goes, valence band goes above, so this is shown here in red, so it goes above up here, but normally it's much higher, above the Fermi energy, and correspondingly the conduction band goes below the Fermi energy, then they overlap and electrons can freely move from the valence band where they were frozen to the conduction band, okay, where they can move freely. And as a result, these materials have a high electrical conductivity, okay? This is the case for metals. Now, in semiconductors and insulators, the valence band is almost full, And so because all electrons basically sitting below the Fermi energy, and they cannot move to the conduction band here. But for semiconductors, there is a gap between valence and conduction band is very small, okay? And occasionally some electrons can jump from the valence to the conduction band and provide, and they just give to semiconductor some electrical conductivity, okay? Much less than in metals, but they can still jump, okay? And in insulators, correspondingly, this gap is very large, very large. As a result, the probability for electrons sitting in the full valence band, fully occupied, probability is very small, and conduction band is empty, no electrons to conduct electricity, and so electrical conductivity of insulators is very close to zero. Okay. So what we are going to look at, we are going to look at the case of semiconductors and to understand the electrical conductivity better. So assume that at T equal to 0, the valence band is completely full under the Fermi surface, and the conduction band is completely empty. Okay, almost, yeah. This is what we call the natural semiconductor. For a moment, because temperature is 0, they cannot jump from here. No thermal fluctuations. Temperature is 0. As the temperature increases, thermal fluctuations will cause some electrons to be excited across the gap, because the gap is not that large, leaving holes in the valence band, as I explained before, and creating particles in conduction band. So these particles and holes, they behave like free charge carriers, and the system exhibits electrical conductivity. We can approximate the dispersion curve. So the energy of these particles, depending on their wave number, by the following picture. Normally, when there is no gap, we expect this dispersion curve to be approximately quadratic. The energy is approximately proportional to the wave number. But there is a gap here when energies are not allowed. Okay, so no energies in this area. So the real dispersion curve in this case looks like that. So it approaches then the low side of the gap, the lower side, and then it's smoothing out, okay, like that. And the same picture, that there is a deviation from the dashed line from the above in the conduction band, and then dispersion curve, it's smoothed out. So we can approximate the smooth pieces here, deviation from the quadratic dispersion curve by parabolas. Okay, it's a good approximation. You see that this is a typical experimental picture, and you can see that we can indeed approximate it approximately here by parabolas. That's a good approximation in the neighborhood at the top of the valence band and the at the bottom of the conduction band. So here's the picture. So the energy of an excited electron near the bottom of the conduction band is in here, can be written if the top of the valence band is epsilon 0, then the bottoms of conduction band plus delta, and plus approximately kinetic energy, a quadratic term, plus some quadratic term in the momentum. And we write this quadratic term as p squared over tmc, where mc is the effective mass of the particle in the conduction band. Okay, and similarly in the valence band, the energy of an empty state just below the top of the valence band is given by the energy minus p squared over 2m valence, where the m valence is the effective mass of the basically of the whole of the missing particle. It's and there is a sign minus, so there is a hole with a negative energy, and so effectively it's the mass of the particle below the valence band. Okay, below the top of the valence band. So we know that density of particles and holes, we can write them down simply as we did before. Here's the occupation number for particles, and here the occupation number for holes with opposite signs of mu and the energy. And then integrating over the momentum space, we can derive occupation numbers and occupation numbers of particles above the gap and holes below the gap by these formulas. Now, because temperature is low, so beta is large, so we can assume that these two quantities here are large. Okay, this is a quantum regime. So in this case, we can discard this plus one here and approximate these expressions by exponents. And then this integral is just a Gaussian integral, which can be calculated explicitly, and here is the answer, this integral. And by the way, the factor 2 here, remember that our particles are fermions, and they can have two possible orientations of spins, up and down. So when we count in the occupation numbers, integrating over the densities, then over the all possible momentum of particles, then there is an extra factor 2, which corresponds to the spin 1/2. So approximating these integrals at low temperatures or high betas, we get the following expression, and this is two expressions for densities of particles and holes. Now, overall electrical neutrality requires that number of particles in the conduction band should be equal to the number of holes in the valence band. Okay, because basically we expect that the number of particles escaping the Fermi surface is exactly the number of holes creating under the Fermi surface. Okay, so we can, so these two densities should be equal, and so if you look at this equation, then if you just make that equation to be, you see that chemical potential here, it enters with plus sign, here with minus sign. So if you write the equation this equal to this, you can express out of this equation the chemical potential. Okay, and the chemical potential becomes equal to this expression. And if we assume approximately that the particles in the conduction band and the valence band, they are equal approximately, okay? So electrons effectively, when they are above the gap and below the gap, their effective masses in conduction valence band, they are the same. This contribution is equal to 0, and we see the expression for the chemical potential. And let me remind you that at t equal to 0, chemical potential is equal to the Fermi energy. So it implies that at t equal to 0, Fermi energy sits exactly in the middle of the gap, okay, in this picture. So here is the gap, here is epsilon 0 plus delta. So at absolute 0 or near close to absolute zero, Fermi energy is exactly in the middle of the gap. Okay, this is what just we derived. So this is approximation. All our approximations are valid if beta delta much greater than 1, low temperature regime. So if you now use this expression for the chemical potential in one of those equations, which should be equal density of particles and holes, then we get for density of particles or holes this expression when we substitute this mu into the previous expression. And this is the answer basically for density of particles or holes in the semiconductor. And for example, if you take a typical value of the gap 0.7 electron volt and mass to be mass of the electrons, we see that at room temperature we get number of particles approximately 10 to the 13th over the cubic centimeter per cubic centimeter. Okay, but a typical charge carrier density for a metal is 10 to the 20. So the number of particles which can carry charges is like by 7 or even more 10 orders of magnitude less than in the metal. So the electrical conductivity of a natural semiconductor is really negligible. It's 7 or 10 orders less than the electrical conductivity of a metal. Of course, electrical conductivity of insulator, it's even like 20 orders of magnitude less than a metal. So it basically has zero conductivity. But you see that in natural semiconductor, it can conduct current, but its conductivity is really low. Now, examples of natural semiconductors are silicon or germanium, and they all have 4 electrons in its outer orbital. And these electrons bond to 4 neighboring atoms, forming a lattice. There are no free electrons. Okay? But if we introduce impurities into a semiconductor, which is called a doping process, we can greatly increase electrical conductivity of semiconductors. Natural semiconductors, now they called doped semiconductors. For example, when we add pentavalent atoms, which have 5 free electrons, or donor atoms, phosphorus, arsenic, examples are as an example, then these pentavalent atoms, they will bond 4 electrons with atoms of silicon, but they may give 1 free electron to a semiconductor. Okay, so 1 electron out of 5 cannot bond, and as a result, there will be free electrons in the semiconductor. This results in an N-type of negative semiconductor. When we add as so-called trivalent atoms or acceptor atoms, which have only 3 electrons in their outer orbitals, they can bond with silicon atoms, but as a result, there will be 1 broken bond, because 1 bond in the silicon cannot bond to these acceptor atoms, and it will become a kind of a broken bond or a missing electron. Okay, this is the same as these trivalent atoms. They create a hole in the semiconductor, a missing electron. This results in a p-type semiconductor. Okay, adding different impurities, we can create an NP junction, a diode, NPN or PNP junctions, transistors, which possess unique electrical properties. Okay, the question is how many this doping or acceptors, donors or acceptors atom we need to add to a natural semiconductor to ensure that we have a really good electrical conductivity. It appears, that the number of atoms is really small. Actually, it's enough to add one donor and acceptor atom per 100 million atoms in the semiconductor. Okay. So what happens when we add these donors or acceptors? In the N-type semiconductors, the corresponding so-called donor levels, there will be donor levels where these electrons will be sitting. They are free extra electrons, and they so-called bound levels, they will lie exactly below the bottom of the conduction band, below by a small energy, much less than the gap. And they are filled with electrons at T equal to 0, these donor levels. Okay? As the temperature increases, these levels donate electrons to the conduction band, which was originally empty and which can serve now as conducting electron. In p-type semiconductors, the bound levels or holes corresponding to those trivalent atoms, they will lie exactly above the top of the valence band by a small energy gap delta, which is much less than the energy gap. Okay. As the temperature increases, this level accepts electrons excited from the valence band. So electrons, because they have it's like a broken bones or holes, so they accept electrons from the valence band, leaving holes behind in the valence band. Okay, and they create holes like positive charges. We can move in the valence band. So let's calculate the density of electrons for the N-type semiconductor. We will measure the energy with respect to the bottom now. Not previously we measured it with respect to the top of the valence band. Now we measure it with respect to the bottom of the conduction band. So I assume that the energy of the bottom of the conduction band is 0. Okay. Then the donors levels, they will have energy minus delta. So assume that there are n d bound states or donor atoms per unit volume of energy minus delta. Then at 0 temperature, when we increase the temperature, then the density of electrons in the donor levels at temperature T will be equal to this, which we calculated before, which we know that's so when temperature is 0, this fact disappears, it becomes very small, and we get N2 is two spin states, up and down. Okay. Now, number of particles in the conduction band we already calculated before. But before we set in that formula, because before we measured energy with respect to this level, and now we measure it with respect to this level. Okay, so all we need to do, we need to shift this energy epsilon by minus delta, or to set in previous formulas epsilon is 0 plus delta, where we calculated the number of particles in the conduction band. Okay. And this is what we get. This is, if you look at that formula we derived before for particles number, set the epsilon 0 plus delta equal to 0, then we get this number where lambda is given by this number, and z is the fugacity. Since electrons in the conduction band were excited from the fully occupied donor levels, so electrons in the conduction band, they just here, they were excited from the donor levels, basically free electrons from those pentavalent atoms. Then we should have that number of particles plus number of donors should be simply equal to 2nd, number of donors, okay, with spin 2. So with two orientations of spins up and down. So adding these two equations together, we can solve it with respect to the fugacity or chemical potential, and this is the result for the fugacity. Now, if you calculate this result for the fugacity into this density of particles in the conduction band, we get the density of electrons in the conduction band becomes this. So if you expand this expression for small temperatures, as the temperature rises from absolute zero, the particles in the conduction band initially increase exponentially, like exponential of minus delta. This is the exponential factor, and that which is given by this, and this t to the 3/4 comes from this factor. But they flatten to a plateau at 2n density, where basically all electrons from donor levels just go to the conduction band, and all donor levels are depleted. Okay, so the particle density as a result can be adjusted by changing density of donors here. Okay, so you see that we now have a number of donors entering this formula. So we can adjust the particle density in the conduction band by changing this number. And it's sufficient to add only one donor atom per 100 of millions of atoms in the semiconductor to achieve electrical conductivity similar to metals. Okay, it's quite amazing that this correction when nd equal to 0, this is expression is just when nd goes to 0, this number of particles we calculated before. So in the semiconductor, but this is the corrected formula with number of donors, and we see that once we add the donor, only one donor, we can achieve a very high electrical conductivity. And similarly for p-types semiconductors, we can create very high concentration of holes with just only one acceptor atom per 100 millions. Okay, a similar form. And as a result, we can create a diode, as shown in this picture, and it will have only one side conductivity. Because, for example, when we let's assume that we take two semiconductors now of p-type and n-type, okay, of n-type and p-type. When we join a battery to this junction, all electrons want to go in this direction, all free electrons in the n-type, because they will attract to the plus, and all holes will want to go in this direction. And there will be no current across the junction. If we now change a polarity of the battery, then all holes want to go in this direction and all electrons will go to this direction. And at the junction, they will annihilate each other, and as a result, there will be a current. Okay, so a diode is one direction, kind of has a one direction conductivity. If you now connect P and P, P and another P here, or the other way around, and PN, you get transistors. And you know that transistors the main role in all electronic devices. Okay, example problem. Consider a band gap of silicon, and it's known that it depends on temperature. Like here's the size of the gap in silicon, experimental result, and its dependence on temperature. It's approximately 1 electron volt, and there is a T equal to 0, and there are corrections of a very small order of magnitude. You see 10 to minus 4. And his temperature is measured in kelvins. Okay? Find a concentration of electrons in the conduction band of undoped silicon at 77 kelvins. If we know that at 300 kelvins, it's approximately, how many? It's 1000, 10 to 10 per cubic centimeters. Okay, 10 millions. So, but we know that it's really small for a natural semiconductor, but once we add some donors or acceptors, it will be really high. Okay, so let's introduce some effective density of states in the conduction and valence bands. So we know that concentration of particles in the conduction band, and once we start increasing temperature, we calculated it before, and concentration of holes in the valence band given by these two formulas. Okay. Now we expect that number of particles should be approximately equal to number of holes. Okay, so if you assume that particles, once we start increasing temperature, then all holes are formed as a result of jumping fermions. So we expect that as many fermions left, that many holes was created. So this should be approximately equal. So if we multiply them, this is approximate concentration of particles or holes. So n squared, if you multiply these previous two formulas and those previous two expressions, you get this expression. If you substitute everything, you can get a dependence of this concentration or density of particles or holes as a function of temperature. Okay, so this is a function of temperature. Now the question asks, if we know it at one temperature T2, 300 kelvins, what would be that concentration at temperature T1, 77? And for that, we write down these two expressions for T1 and T2 and divide them. And as a result, we can a ratio of two concentrations for T1 and T2 will be a ratio of two parts in the right-hand side. There will be some constant which will cancel out. As a result, we can express the concentration at one temperature in terms of the concentration at a different temperature by simply writing this equation for two temperatures and dividing them by each other. Okay. As a result, once we know a concentration at one temperature, we can calculate the concentration at another temperature. And so if you substitute here T1 equals 300 kelvins and concentration was 10 to the power 10, then at the temperature 77 kelvins, concentration becomes 10 to minus 20 electrons per cubic centimeters. Okay, so once we lower the temperature by 200 degrees, silicon from a natural semiconductor becomes a full insulator. Okay, so at low temperatures, silicon is not really useful as a semiconductor. Okay, so this is basically the end of the lecture on Fermi gas.